Assalamu alaikum everyone. This is lecture 12 of Control System Engineering 1. Today we'll be starting a new chapter, chapter 5, reduction of multiple subsystem. So far, whatever we actually have seen is that we have a single block and we have a system inside, say g of s transfer function, and then just we have input and the output. So input can be r of s and the output can be c of s. So for this is what we have seen, but more complicated system actually can be represented with the interconnection of many subsystems. So this can be one subsystem. Okay. Similarly, a large system like aircraft or radar system, there can be a multiple subsystem possible, and they're interconnected. They're represented with the interconnection. Okay. So far, whatever the knowledge that we have gathered from chapter 4 is that we can find out actually the transient response of a system, something like this. Okay, so a single transfer function we have, and if we apply the test signal, say your step signal, then we may know how the system is going to behave. Okay, so if we want to apply the knowledge that we have gathered from the previous chapter to a system which have multiple subsystem interconnected, in that case, somehow those multiple subsystem that we have in a different pattern of interconnection may be possible. So in that case, we have to reduce all of this into a single block diagram, single transfer function with an input and output condition. Okay, so something like this. Only then actually we can also apply the analytical techniques that we have studied in the previous chapter for the system. So when in this chapter we will try to focus on the technique that how can we reduce multiple subsystems, a system with multiple interconnected subsystem into a single transfer function. So that actually can be done in two ways. The first method is known as block diagram. So block diagram, block diagram, or it can be done using signal flow graph. Okay, so in general, actually block diagram is used for frequency domain, and signal flow is used for state space representation. But this is not rigid or limited only to, but both of them can be actually applied to the frequency domain. So that is why, since we haven't studied the state space representation, so we are going to apply both the method for signal flow for the frequency domain or Laplace domain transfer function. Now also in the signal flow graph, what is signal flow graph? We'll be discussing this thing in detail later on. So in the first part, we'll be seeing the block diagram reduction. Then we'll also see how signal flow graph can be used for reducing the multiple subsystem into a single system. Now, for the block diagram, some of the parameter we already have seen, but we also may need to have some other additional parameter. So the two additional parameter, first of all, we need signal. So we already know the signal like input and the output, those are the signal. Then we have system, the transfer function in the box is your system. Then the two additional one that is required, one is called summing junction. Summing junction. And the other one is called peak off point. Peak off points. Okay, so signal systems, summing junctions, pickoff point. What is signal or how it is represented? Very simple with arrows like RS, like your CS. How the system is represented? System is represented by a box, let's say G of S or H of S, G1, G2, something like this. Okay, so third is the summing junction, which is a new concept. So in the summing junction, what happens is all the output will be summation, algebraic summation of different types of input. Okay, so say that for the summing junction, we have something like this. We have three input going to a junction. So three separate input. Okay, three separate inputs. Say this is R1 is one input, R2 is another input, and R3 is another input, and the sign can be different like plus, plus, minus, or plus, minus, plus, whatever you like. So any addition or subtraction can be used. So what will be our output? So output will be the summation of the all three. So basically it will be equal to R1s plus R2s minus R3s. So this is what the summing junction looks like. The output is the algebraic sum of different inputs attached to that junction. And then the pickoff point. So pickoff point is a point that actually distributes. Sometimes this happens because of the touch sensitivity of the tab. Okay, so pick-off point. So what is pick-off point? Pick-off point is basically if we distribute the input signal into several output, then this is what is called pick-off point. So let me actually draw one figure, then things will be clear. So say we have an input R of S. Now we want to distribute in different lines, different points. Say all of the three will be then RS. Okay, so this is what is called pick-off point. So you may be thinking, then why is it very is a new concept? But if you recall, in our feedback example of the feedback that we have given in the one of the first class was something like this: G of S. Then this is your output. Then from here another point is actually generated H of S. Then it goes there. Okay, so RS, this is plus, minus maybe. So now as you can see, one line is going in this direction, the other line. So this is also a pick-off point. So both CS is actually going to both the line. So this is also nothing new. Now let us start with some common forms that we have in case of the block diagram reduction. So the first form that we have is called cascade form, cascade or multiplication form, cascade form. So say we have for the cascade form, we have a pattern like this. Say this is your G1S, then you have G2S, then you have G3S. So a system with something like this. This is your input RS and this is your output CS. So how can we actually reduce this multiplication subsystem into a single block? So basically for that you can actually use a simple idea. So what will be the output here? Say output here is, we can say that this is x1. So x1 can be multiplication of the two blocks, so basically RS times G1S. Now what about the output of the second stage maybe, and we can say that this is x2. So the previous stage output, so x2S will be x1S times your this block here, so that is G2S. Okay, so what is x1? X1 is nothing but R1s into G1s into G2s. Similarly, the final one, we can say that the output should be equal to actually the X2s input of that one into the transfer function G3s. So if you put the value of X2s, then what you are going to get is R1s, then you have G1s, G2s, and G3s. So this is your output. So output by input is should be your equivalent transfer function. So C of S by R of S can be actually said that G1s, G2s, and G3s. Okay, so and this is also, you can say that our equivalent model G equivalent of S. So if multiple blocks are in this cascade form, then actually we can multiply them together to find out the equivalent transfer function. But we have to keep in one thing in mind. We have to keep one thing in mind, that the interconnection connected systems should not be loading the adjacent subsystem. So what does it mean? So if one of the block is loading the next block, then this multiplication form is not valid. That is, a subsystem's output remains the same whether or not the subsequent subsystem is connected. Okay, so if you're connecting the blocks, if your transfer function is different, so you know the transfer function of each of the block. So if you multiply those two and you say find one result, and if you connect them and then you find another result, then actually the one system is loading other system. So in that case, we cannot apply this cascade form. So let us give one mathematical example that will make things easier to understand. Say we have one block, something like this, uh, resistor and the capacitor network. Okay, so say this is your VIS, this is your V1S, this is C1, and this is your R1. So we can definitely say what will be the transfer function of this one. The transfer function of this one is G1S, say equal to VI, output voltage is VIS divided by input voltage, V1S divided by VIS. Now, if you figure out the transfer function, so actually voltage divided. So this impedance divided by the total impedance. So 1 by C1S divided by 1 by C1S plus R1. Okay, so if you simplify a bit, so what we are going to get here is, if you multiply, there it is 1 plus R1 C1S by C1S, and also in the numerator you have C1S, so C1S getting cancelled out. So what we are getting here is 1 by R1 C1S plus 1. But we generally don't keep the coefficient of your S, so we can divide it. So now what we will get, 1 by R1 C1 S plus 1 by R1 C1. So similarly, say after this block, we have another block, and we're assuming that the voltage of this one is actually going to apply to the next block. Say that we are also assuming that this V1 is the source of the next branch. So say V1, we are just assuming that ideally it is also a voltage source, the voltage here. So V1S is going there. Okay. So this is your R2, then this is your C2, then this is your V2S. Similarly, if you try to find out, the transfer function for this module, Similarly, G2S will be, if it is ideal source, then you will have similar idea. So I'm not going to derive it because you know the derivation will be similar thing. So we'll have 1 by R2 C2 divided by S plus 1 by R2 C2. Now, if one branch is not, one subsystem is not loading the other subsystem, what does it mean? That is that if you just multiply this one, so it should give you the equivalent transfer function G1, G2S, even if you connect or do not connect the branches together. Okay, so now say separately, these are the two transfer functions. So if you multiply those two, say what we are going to get is 1 by R1, R2, C1, C2 divided by S square plus 1 by R1, C1 plus O1 by R2, C2, S plus 1 by R1, R1, R2, C1, C2. So this is the transfer function simply by multiplying these two. So this should be equal even if you, this should be valid even if you connect the two subsystems. Like if you have connected both the subsystem, okay. Okay, so they say this is your R1 C1, this is your V1S, this is your V2S, this is R2 C2. Now, now if you find out the transfer function of this one, G, say connected network, say S, this one will be actually V2S by VIS. Now, if you solve for this one and still you get the same transfer function, that means both the condition is valid, whether the network is connected or not, it possesses the same transfer function. And in that case, we can say that the networks are not loading each other. And then your cascade form is valid. So multiplication is valid. But let us try to figure out what is actually the transfer function of this one. Okay, so we can go for the mesh analysis, we can go for the nodal analysis. I'm going here with the nodal analysis. So say V1, we are applying in this node first, V1S minus VIS by R1 plus V1S by 1 by C1S plus V1S minus V2S by R2, and that should be equal to 0. The first node equation. The second node equation, node 2. So for that one, we can write that V2S minus V1S by R2, okay, plus V2S by 1 by C2S, C2S should be equal to 0. Now we can write that V2S minus V1S by R2. We can just multiply plus C2S V2S equal to 0. So you just multiply with R2. So V2S minus V1S plus R2 C2S V2S equal to 0. So from here, if we can find out what is the value of V1S, then if we can replace the value of the V1S into the first equation, then we should have the relation between the input and the output. So V1S can be written as V2S can be taken common 1 plus R2 C2S. Okay, so now we know the value of the V1S. Now if we replace the V1S into the equation 1, And I'm not sure whether I should go with the derivation. Sometimes it's become way too complicated, but leaving you in the middle is also not that good. So that is why I sometimes go with the derivation. But maybe if you can suggest me whether I can directly write the first equation so that the derivation you can do it by yourself. Okay, let us continue in this time, but I'll be waiting for your feedback. Okay, so now here, if we replace the value of the V1, so what we are going to get is V2S 1 plus R2 C2S minus VIS divided by R1 plus C1S can be multiplied. So C1S into V2S 1 plus R2 C2S plus V2S 1 plus R2 C2S plus minus V2S by R2 equal to 0. Okay, so as you can see here, we can actually simplify because this first term can be subtracted from this V2S. So this first term can be subtracted, and with the second term there should be a V2S. Okay, so this is what can be applied, and also this is R2, this R2 and this R2 can be cancelling each other. So we can simplify a bit. So what we'll have is V2S plus V2S R2 C2S minus VIS by R1. Then you have plus C1 C1S V2S plus R2, just multiplying together in the second term. So what we will have is R2 C1 C2 S square, then V2S. Finally, the last term, that after simplification, what we are having is C2 C2 S V2S. So now this R1 can be multiplied throughout the equation. So we can write V2S plus V2S R2 C2S minus VIS. Then you have plus R1 C1 S V2S. Then you have plus R1 R2 C1 C2 S square V2S plus R1 C2S V2S equal to 0. As you can see, there is only one input term here. Rest of them actually output term. So you can easily take common of the V2S from one side, and we can set the VIS into the other side. So say VIS we are sending to the other side, and in the V2S, as you can see, there are some S terms. So actually this is S. So this is a one S term, this is another S term, this is also S term, and this is S square, and this is simply VS. So if you take common of the V2S, what you are going to get is R1, R2, C1, C2, S square plus R1, C1 plus R2, C2 plus R1, C2, S plus your 1. Okay, so if you now try to find out the transfer function, so V2S by VIS, then you have to divide by this whole parameter here. And also we cannot keep the coefficient of the highest order of s. So you have to divide the numerator and the denominator by this factor. So what you will have is 1 by r1, r2, c1, c2. Okay, so then you have s square plus, if you divide this one by r1 and r2, then you will have r1 and r2, 1 by r1 and r2. Also a, 1 by R2 and C2, and for this one we will have R1 and R2. So you can simply write something like this: R1 C1 plus 1 by R2 C2, and plus 1 by R2 C1 S plus 1 by R1 R2 C1 C2. Okay, so now if you try to compare uh, this equation with the other equation here that we have multiplied previously. Okay, so I think here. Okay, so this term and this term is okay. There is only two terms here, one by R1 C1, one by R2 C2. But here we can see that we have rest of the parameter is same. This. This is an additional parameter. So what we can say that G equivalent, which can be obtained from the multiplication, is not equal to the G connected network. So one branch is actually loading the other branch. So one subsystem is actually loading the other subsystem. So that is why the cascading cannot be applied for this particular network. So if you want to still apply this cascading thing to this particular network, then what you have to do is very simple. You have to put one amplifier in between, let's say like your operation amplifier. So what are the properties of the operation amplifier? The properties of the operation amplifier is, so this is your amplifier K. Okay, so the properties of your operation amplifier is it has infinite, Z in is actually infinity, very high input impedance. What does it mean? There will be no current flowing in this way, I should be zero. And what is the other characteristic? Z out should be zero. So it will be just acting like a voltage, say, as source from this side. Okay, so one branch is not actually loading the other branch, but this will actually have an impact as a gain. So if your amplifier has a gain K, so your equivalent network will have V2S by VIS equal to K will be added, K into G1S into G2S. Now, for simplicity, if your gain is 1, then the K can be 1. So and your problem is solved, no gain. Okay, but if you say that you need some amplification of your signal, that is also possible through the value K. So while you are applying this cascading formula, you always have to keep in mind that one branch should not be loading the other branch, otherwise this cascading cannot be applied. Okay, so this is the form 1, cascade 1 that we discussed. Now we go to the form 2, the second one, that is called parallel form. Parallel form. So in the parallel form, we'll have something like this. All the branches starting and the ending point is the same point. So say you have a gain G1S here, and then you have a gain G2S here. You have a gain G3S here, and okay, so this is your RS and this is your CS. Now, how can we simplify this branch into a single transfer function? So all of them starting point and the ending point is same. So this is also one of your pickoff point. So now what will be the output here? And also the sign may be different, like plus minus. It can have both signs. So whatever it is, so it will be same. So say this is your x1, this is your x2, this is your x3. So what is x1? Output x1s is basically the transfer function rs times g1s. So x2s is rs times g2s. Okay, so G2S. Similarly, your X3 will be X3S is your RS time G3S. Is it okay? So now after that, you just have to add those. So your summation will be actually based on the sign, actually plus minus X1S, plus minus X2S, plus minus X3S. Okay, so instead of this three block, we can actually write a single block, and the consequences that is going to be, so if you add these three and you take RS common, so you are going to get plus minus G1S, plus minus G2S, plus minus G3S, based on the sign of the summing junction. So this is your RS and this is your CS. Okay. So we can say that our equivalent transfer function will be plus minus G1s plus minus G2s plus minus G3s. Okay, so this form is slightly simpler than the previous one, so we don't have to bother about the loading thing. Okay, next and the last one is feedback form. Feedback form. So in the feedback form, in the chapter 1, we have given one generalized feedback, something like this. Say this is G1S, then you have a summing junction, then you have G2S, then you have G3S. In the general, in the feedback path, we call it H. So say H2S, and then you have H1S. Okay, so this is your CS. So now this is your RS input with more generalized version. So input, then you have this may be input transducer, input transducer. So if your signal is not electrical, then you need some device to convert to electrical domain. Then this signal here, E, is actually known as actuating signal. Actuating signal, or sometimes error signal. And this may be your controller. First G here, controller, and this may be your plan, the system that you're trying to change, control. Okay, so plan, and it may be the H1 may be your output transducer. So output transducer. So if your output is also not electrical domain, then it has to be converted to electrical, then you can use it. Then you can also have maybe the feedback, adjustment of the gain or something like this. So this is a more general type of feedback, but for derivation, we'll be looking at a simpler version. So say that our simpler version only has, after multiplying the G2 and G3, we just have a simpler version like this. So simpler version is, say you have input and going to the summing junction, then you have 1G, G of S, maybe plant and the controller. So multiplication of that, then you have one feedback. So let us try to derive the equivalent model first, then we can have multiple component in each branch. Okay, so CS, and then you have your RS, also the error signal, yes. Okay, so the error can be, the feedback can be negative or positive. Okay, so now what will be from this block diagram? What will be your, this is always positive, so what will be your error signal? What we are actually interested about to find out a relation between your RS and CS, okay, with a single block. So this is what is our intention out of this feedback network, to find out the relation between CS by RS. That is your equivalent model. So now for that, let us try to see what is E of S. Now E of S can be written as RS, some RS is positive, then minus plus, then this signal. What is this signal? This is just multiplication of this one and the output that is coming. So basically, CS times HS. Okay, so again, what is CS? We can see that we have a signal ES here, which is multiplying with GS, then we're by finding the CS. So we can say that CS is actually nothing but ES multiplied by your G of S. So we can replace the value of ES, which can be written as CS by GS, and we can put it into this equation. So what we are going to get from this equation is basically CS by GS equal to RS minus plus CS HS. So if you cross multiply, then you have CS equal to RS GS, then minus plus CS GS HS. Okay. So now we can take the CS into the other side. So the sign will be altered. Minus will be plus, plus will be minus. So we can take common CS. So 1 plus minus G of S, H of S equal to RS G of S. So we are interested about the relation of C of S by R of S. So this will be going the other side. So what we'll be having is G of S divided by 1 plus minus G of S, H of S. So what you get is we have an input-output relationship, and that block feedback block diagram can be reduced into a block like this, G of S divided by 1 plus minus G of S, H of S. Okay, so this is your CS, this is your RS. Now, whether you noticed or not, we had a system something like this, G of S, a feedback which was negative or positive. So H of S, negative or positive, and plus RS CS. So if the value is negative here, then you will have a positive sign here. And if the value is positive here, then you will have a negative sign here. This is one thing to notice. And also try to remember in this, this is forward path gain, G of S, and this is feedback gain. So the formula is forward path gain divided by 1 plus forward path gain into feedback gain. So that will be your equivalent network. Okay, so these are the three common forms we will encounter while we try to reduce we try to find out our transfer function. So one thing also sometimes is known as this particular gain is also known as loop gain, because this is a gain of this loop. So this is also known as loop gain, loop gain. Okay. Okay, so loop gain or open loop transfer function, open loop transfer function, transfer function. Okay, so this is an alternative G of S, H of S, which is known as loop gain or open loop transfer function. So three form we have studied. One is cascade, one is parallel, one is feedback. So sometimes if you can directly identify in a interconnected system which one is available, then we can apply corresponding formula, corresponding equivalent model to reduce the block diagram. But sometimes it is difficult to identify which one is available because of some branches in the middle. So that is why it is prescribed to know how can we move the blocks from one side to another side of a pickoff point or the summing junction, so that we can bring those familiar forms that we know, or this basically these three form: cascade, parallel, or feedback. So let us try to look at this uh, two cases for summing junction, as well as two cases for your pickoff point. Say we have something like this. We have two signal getting added. Then this two signal is being multiplied with a gain G1S. Then we are going to get our final outputs. Yes, so this is your R1S and this is X1S. Just say, so now somehow because of this block, if it is difficult for us to apply the simplification, so somehow can we bring it to before the summing junction? It can have plus or minus plus, something like this. So how can we bring this branch to this side? Okay, so equivalent model. So is it possible? So because they will be actually added together, this one and this one, then it will be multiplied. Both the signal will be multiplied by G1. So you can actually prior multiply both the signal with G1, then actually you can add them together as well. So this can be easily done. Okay? And this is remaining same output. So output is also not getting changed. So R1 is X1 is. So both of them is multiplied by G1s. Okay, so this is how you can move the block from after the summing junction to before the summing junction. But net result is not going to change. So this is one case. So the other case, maybe we can say that one signal is actually multiplied with one gain only. And then you have the summing junction, say plus minus something like this, and this UX1S. Now somehow say that we have to bring this block to the other side. So is it possible or not? Okay. So if you want to block it and how the system can be. Now if you bring it here in the other side, definitely both the signal which will be added together will be multiplied by G1 because they are common to both the signal. So G1S. Okay, so will your output remain same for both the signal, because only R1 is getting multiplied with this one. So this one is not supposed to be multiplied with this one. But if you bring this branch to the other side, then both the signal R as well as X will be multiplied. So what you have to do to make the thing same as before, you have to divide by 1 by G1S. Then actually you can uh, send it to the other side. So this one and this one will be cancelling each other. Eventually X will not be multiplied by the G1s. So this is how you can move the block either from the outside to the input side, output side to the input side, or from input side to the output side. So that we can actually bring those familiar forms like the cascade, parallel, or feedback, so that you can easily apply those simplification. Then we have say now these are the example of your summing junction. Now if you have pick-off points, so can we apply something like this? So say we have one pick-off point and three terminal is coming out, and these two are not multiplied with any gain, so this is just remaining RS. This is also remaining RS, but this block is actually multiplied with GS. Okay, so this is RS. So this is what is becoming RS and GS. Now, which will be now if you say that we want to bring this branch, this box transfer function into the input side. So then what will be your equivalent model? So I think you already guessed it. So only one branch should be multiplied by this one, GS. But if you bring it here, then all three will be multiplied. But these two are not supposed to be multiplied by them. So there has to be divided so that it remains same. So we can actually have something like this. GS, then you have RS. Actually, you have to be careful about the arrows as well. So now the first one will be always having RS G of S. But other two, if you directly give this, then they will also have RS GS, but they are not supposed to be, they are supposed to be RS. So that is why they has to be divided by 1 by G of S. So now they are RS, and this one is also be the same. Okay, so this is also RFS. So this can be one thing. So the other thing can be something similar. So now you have one block here, G of S, and this is your RS. So say all three are actually say same thing. Okay, so all three is basically RS, GS, RS, GS. So in this case, what can be done equivalently? Uh, Actually, this one can be brought here, here, here. So we can easily move to all three branches. So it is actually easier compared to the previous one. So you will have the gains in each branch, something like this. So same thing. So this movement of the blocks will actually help us to figure out to find the similar forms or familiar forms, so that actually we can easily apply our formula. So let us try with one example. Example 5.1. So in the example 5.1, I'll be trying to go a bit slow so that you can catch the ideas that is being inherently given here. So we have one box GS, one system, then you have three consecutive summing junction, then you have G2S, then you have G3S, CS. Okay, so say we have one gain H1S here, another gain H2S from the same node say, and also another one is here H3S. Okay, so they have given this sign, so this is your RS. They have given this is positive. They have given this one is negative. This is positive. This is negative. And also these are positive, positive. Okay, so arrow should be there. Now we have to reduce this multiple subsystem transfer function blocks into a single transfer function. So first thing, if you are given this any problem, what thing you have to see is that what are the things that can be, if there is any familiar form available or not. So this is what you have to identify first thing. Okay, so then you have to start applying. So now first thing that you can see is this two are in cascade form, so they can be multiplied together. And also, as you can see, there is three summing junction, but summing junction can be added together. Okay, so this is something new for you, but actually, if you have all the three coming from to the same junction, it is also not a big problem instead of three summing junction. So all three can be also grouped into a single summing junction. So these are the two things we can straight away apply. So first thing let us apply is G2S and G3S multiplied together. So cascade form. So they have been, now we have one single block. And second thing is we can apply one junction instead of three. Okay, so what we can do here is one will be coming out from here, maybe one from here, one from here. So this is your H1S. This may be your H2S, H2S, and the other one may be your H3S. So one thing you have to be careful what sign you are going to put. So CS, then you have another gain, G1S, then you have RS. So now one thing that you have to be careful is what sign, this sign is positive, no problem. But now you have to be careful about the sign that you are going to apply here. Okay. So the first one is negative, so negative. The second one is positive, positive. The third one is negative, negative. Now, as you can see, their starting point is same, and all three branches ending point is the same summing junction. So actually, these three branch can be said parallel. So parallel things actually additive. So what we can say now, it is critical now which sign you are going to pick. So in general, we prefer a negative feedback. So we keep it negative feedback. So one single negative feedback. So that means this one will be, if you take negative feedback, this will be positive, this will be negative, and this will be positive. So we have G2S, G3S, and because of the negative feedback, negative ones will be positive and positive one will be negative. So we can write H1S minus H2S plus H3S. Okay, so this is your, now I think you already recognize this is a feedback branch. So now you have a negative feedback where your forward path gain is this one, and this is your feedback gain. So what we know for the negative feedback is forward path gain divided by 1 plus forward path gain into feedback gain. So this is the formula that you know. So how big the quantity is, the same formula that you have to apply. So what we can get is RS, keep the G1S as it is for now. Now this whole branch will be, the whole thing will be converted into a single branch. So now it will be becoming a single big box. So say this is your C of S, and forward path gain, which is G2S, G3S divided by 1 plus forward path gain G2S G3S into feedback gain, that is H1S minus H2S plus H3S. Okay, so now again the next familiar form that we are going to get is a cascade, so just multiply together. So finally what we are going to get is G1 will be simply multiplied, so G1S, G2S, G3S divided by 1 plus G2S, G3S. Then you have H1S minus H2S plus H3S. Okay, so this is your required single transfer function model. Okay, so this is how we actually have to, if you have multiple blocks, or multiple interconnected subsystems, we have to apply those three forms that we have learned in this class. One is cascade, then you have parallel or feedback. So in that case, you have to use those three format to basically to transform all these block into a single transfer function. Sometimes, in most of the time actually, we'll be facing that it's actually difficult to find the suitable familiar form. So in that case, we actually have to take the help of block movement before or after the peak of points, so that actually we can bring those familiar three forms, so that that can be applied to figure out the corresponding block diagram reaction model. Okay, so this is, I think, even though we should be using a few more exercise to solve this one, uh, I think we already, it's closer to 1 hour so far. So also the last class was a lengthy one, long one. So that is why let me stop here for today, and we'll start with few more example of block diagram reduction, say example 5.2, as well as a skill assessment exercise, maybe the 5.1, and a few other from some other book. I'll try to collect, and then I will also discuss those so that you actually get more familiar with the method of this block diagram reduction. Okay, so I'll try to spend one more class on this block diagram reduction before going into the signal flow diagram. So basically in this chapter, we have only two methods to learn. One is block diagram reduction, which we are discussing right now, block diagram reduction, which is a common one for frequency domain, but both can be applied for frequency domain, and the other one is signal flow diagram. Signal flow diagram. So I want to spend one more class on this block diagram reduction before I go into the signal flow diagram, because of the fact that the more time we spend on this one, the things will be slightly easier. So I'll try to take few other examples from some other book, and then I'll try to cover those things before we go into the signal flow diagram in the next class, inshallah. So I hope this will help you, inshallah. So see you in the next class.